folks. So since we have a snow day, and it's our second snow day, we really can't afford to take another week off. So we'll have to have video lessons this week. So I'm going to teach the second half of Module 11 on video, and then when we meet on the 24th of February, you'll have the first day of Module 12. So watch these videos, and hopefully you've taken the extra practice problems, and then you'll be prepared to take the test for turning in on the 24th, and then you'll complete the first half of Module 12. So hopefully I can get these videos posted quickly so you can not get too far behind and not have such a stressful week. For those of you who are attending Team Pact, you won't be in class on the 24th, so I will have videos up for that class as well. And I hope you have a great time there. And it will be like a month since I've seen you by the time you get back, so that's really awful. So the first thing I wanted to do, since Module 11 is about making solutions, and we never did have a chance to compare how you make a solution using molality and how you make a solution using molarity, that's where we're going to start. So I left all the stuff that we were going to make the 1 molal sodium chloride solution with in the classroom. So what we have here, I have a different volumetric flask, so it's a different thing, but it's the same principle. What's the difference between, and in this case, I'm going to make a 0.50 molal solution of sodium chloride and a 0.50 molar solution of sodium chloride. So when we calculate out how much salt to use to weigh out on our mass scale to make these solutions, what we see is the molar mass of sodium chloride is 58.5 grams per mole. The chalkboard just doesn't let me put everything in, so you know I like to have you write the chemical name and everything, but it doesn't fit in my handwriting so that you can see it on the screen. So this is 0.50 moles per 1 kilogram of water. So clearly that's making the molal solution, because molality is moles of solute divided by kilograms of solvent, which is water unless it's otherwise specified. And I'm going to make 100 milliliters. We know the density of water is 1 gram per milliliter, so that's 0.1 kilograms of water. That'll be 100 milliliters of water. And then I multiply by the molar mass to cancel out moles and get grams. To make the molarity solution, I do 0.5 moles of salt per liter of total solution. That's molarity. And I multiply that by 0.100 liters, because I'll make that in a volumetric flask. And so we'll make 0.100 liters total solution. And I multiply by that by the molar mass of salt. In both cases, I find that I use the exact same amount of salt. Okay, whether I calculate the molality times 0.1 kilograms of water or the molarity times 0.1 liters of total solution, I find that I need to use 29.3 grams of sodium chloride. So before I started the video, just so we didn't fumble around forever, I weighed out 29.3 grams of sodium chloride into my volumetric flask, and I weighed out 29.3 grams of sodium chloride into this, just so I have it weighed out. I'm not going to make the solution in this. So you guys have been with me lots of times when I've made a molar solution. So when you make a molar solution, you just put your solute in, and then you dilute it up to the amount of total solution you want. In this case, I'm going to make 100 milliliters, or 0.1 liters of total solution, because that's the size of the volumetric flask that I happen to own. I left my little 50 in class at the classroom. So here I go. I'm diluting it up. You know, it'd be better to use the wash bottle. So once I get a little bit of water in there, I'm just going to swirl to make sure that all of my salt is going to dissolve. Having an undissolved solution once you get water up into that neck just makes it really hard to shake. And especially if it's something scary, you know, you can't just shake it like that, like I can this salt solution, although I do have a lid. Oh great, spilling water everywhere. Oh. Alright, we have little air bubbles. Oh my goodness, I can't do it.
What?
I need a lab assistant, guys. I hope somebody will be available first period next year to be my lab assistant so I don't have to spill everything everywhere anymore. Okay, so I'll go slow and careful. I'll fill a little more and then try to dissolve a little more of the solid. Okay, so I'm mostly filled here. I didn't bring my extra wash bottle up, so filling it right to the line is going to be really tricky, and clearly I'm not going to hit the line very accurately. When you make a molar solution, you use this volumetric flask because it's a very precise measuring tool, and I'm using it very badly indeed. So, get the edge wiped off. So you surely can't see, but you've seen in class the line right here on the neck where exactly 100 milliliters of total solution is. So as I go to fill it, once you get into the neck, it goes so fast. And if I miss it, you just have to absolutely make the solution again. There's just no recovering from missing the line on a volumetric flask. So I'm swirling. All right, so now I'm going to start filling up in the neck, up over my head so you guys can see. And I want the bottom of the meniscus right on off. Filling, filling. Not going in. This is absolutely supposed to be done with a wash bottle. It's ridiculous the way I'm doing it. Okay, there we go. And you never want to blow in your, if I'm going to use this solution, I'm just going to dump this one out, so it doesn't matter. Oh my goodness, I went over the line a little bit, but assuming the bottom of my meniscus is right on the line, which it certainly is not, I would have a perfect 100 milliliters of total solution of sodium chloride, and it would have a concentration of 0.5 molar. So 100 milliliters of 0.5 molar sodium chloride is made that way. Now, even though you put in exactly the same amount of salt, you make a molal solution in a completely different way. So remember, you have to measure out 0.1 kilograms of water. So much easier than the volumetric. 0.1 kilograms of water is, of course, 100 grams. And 100 grams is 100 milliliters because the density of water is just 1. So I can easily get the bottom of my meniscus right on the line, which I should absolutely do while putting this on the desk. I'm a little over. Well, am I a little over? Alright, I'm going to get my eyeball right down here to, yeah, I'm a little over. So, let's see. I'm a little under. Oh, the challenge. Alright, so that's looking pretty good. I have 100 milliliters of water right here. And when you make a molal solution, you measure the mass of the solvent. In this case, water. Mass is easy because you can measure the volume and assume the mass is correct. And you measure the amount of the solute, in this case 29.3 grams, and you just mix it together. So when I pour salt into the water, what do you see as being, hopefully I can do this and get it dissolved without making a complete mess? Okay, so what do we see as the difference? How can we tell which solution is more concentrated, the 0.1 molar or the 0.1 molal? Well, in the 0.1 molar solution, I have 100 milliliters of total solution, and I put 29.3 grams of salt in. With this, you can see when I added the salt, maybe you can, when I added the salt, see if I can get the light to hit it correctly so you can see, when I added the salt, right here is the 100 milliliter line. So you can see the amount of solution increased, of course, when I added the salt, because I added matter, the volume increased. So I probably have about 10 milliliters more solution, maybe somewhere around 110 milliliters of solution with that same 29.3 grams of salt. Oh dear, my screen turned off. Ooh, I've never used the webcam before, so hopefully it's working. So you can tell that the 0.5 molar solution is more concentrated because it's 29.3 grams of salt in 100 milliliters of total solution, whereas the 0.5 molal solution is 29.3 grams of salt in about 110 milliliters of total solution because of the difference in the way you make the solutions. So just kind of a demonstration of how to make solutions and how molarity and molality are really different. Let's see, is there anything else I wanted to talk about with that? Oh, yes, there is. Okay, so I'm just going to give a quick rinse to this 50. This 50. Okay, so I have, oh, I need to pour that out. Okay, so I have two 50 milliliter graduated cylinders here, and I'm going to fill one with water. And I'm going to make sure I have exactly 50 mils in it. And I'm going to show you why you need to be concerned about total volume of solution. So now I'm going to dump out my salt water here because I don't need it anymore, but hopefully you saw how to make a molar and a molal solution. And I'm going to try to rinse out this mess of salt here. Alright. Hopefully it's not too salt laden. So I have another 50 milliliter graduated cylinder, and I'm going to fill that with rubbing alcohol, which this is 91% rubbing alcohol, so it's almost completely and totally rubbing alcohol. There's not very much water in it, but it will serve our purposes today. So hopefully I can get that right to the 50 and not contaminate my stock. Almost. When you make measurements in the college lab, you want to be very, very careful that your meniscus is exactly where you want it to be, unless you're just doing qualitative analysis and not quantitative. Okay, so I have 50 milliliters of rubbing alcohol and 50 milliliters of water. So when I combine the two, would you expect that to make 100 milliliters of total solution? I would expect that, right? At first glance, you think, well, obviously 50 milliliters of water plus 50 milliliters of water would make 50 milliliters of total solution. And that's just not the case when you mix two different chemicals together every time. So when you're especially doing molality, you're worried about just kilograms of one thing and kilograms of the other thing, or kilograms of one thing and moles of the other thing. And you have to measure and mix and not worry about the total solution volume. With molarity, of course, you're worried about total solution volume in the end. So you have to put in your solute and then dilute up with your solvent. And so hopefully I'm going to be able to show you that 50 milliliters of water and 50 milliliters of rubbing alcohol does not make 100 milliliters of total solution. So let me aim the camera and see if we can watch. Oh, here we go. Okay. So the 100 mil mark is like right here where my thumb is. I'm adding 50 milliliters of water and not spilling. Let's see if they line up properly. So yep, that's right at the 50 mark. And then I add the rubbing alcohol. And I'm going to mix them without spilling, I seriously hope. So we get a good mix. And if you notice, if I can get it to hold very still, maybe I'll tip it up. And can you see? If I get it very flat, we're probably only at 98 milliliters. And I didn't spill anything, so I hope it can really show you that we're a bit under. But total volume is not the 100 that we would expect because of the interactions between the alcohol molecules and the water molecules. They get closer together than they get to each other, or to themselves, when they're separate. So when you mix rubbing alcohol and water, you get actually a little bit denser solution than either one is individually. So that's why you really have to pay attention to how you're supposed to make your solution, because it can really make a difference. So I'm going to start a new video for the actual Module 11, but hopefully that was a quick review of molality for you, and to show the difference between molality and molarity. And I hope you all are having a good snow day, and I will see you soon for the next video.